Alright guys, here we go. Example 1 for linear equations. So let's just kind of like take a step back and ask ourselves like what are linear equations? What does this have to do with matrices? Well, back a long time ago, a lot of mathematicians and so on and so forth, they didn't really use a lot of equations. Everything was done inside of matrices. And this is sort of like an introduction step that will lead you into how to conform matrices, so on and so forth, and how to manipulate them. Because as you can see, these linear equations, while you might be able to solve one for like one, two, three, maybe four variables, when you're dealing with 10,000 variables, it's not gonna be quite useful, and you're gonna spend a lot of time, and you're probably gonna make a lot of mistakes. Matrices are basically the easy way of calculating this, and this will lead you on into that. Now, if you're thinking this topic is quite hard, it's actually also quite old. The credit of using matrices actually goes back to a Japanese mathematician by the name of Sakikoa, and he never really got the full credit for it. Another German mathematician called Leibniz, or Gottfried Leibniz, he actually got most of the credit for it, and differential calculus as well. Actually, him and Newton got the credit at the same time, but the only difference is like one of their main things is like one would have like your first derivative is that, another one would have it as dx dy, so on and so forth. So they represent it in different ways, and that's another interesting story for another time. But here we go, linear equations and matrices. Most of you guys probably already know how to solve this, but let's go through it. We have our two variables, and there's a couple ways we can do this. Since we're not going to be using matrices right now, we just want to solve for the variable itself. So we can either use elimination, or we can use substitution, where we would solve for one variable and plug it into another. I'm just going to do it with a substitution way to make this a lot easier. What we're going to do here is we're just going to multiply the bottom equation by 3. And yes, you can multiply any of these equations individually by any sort of value, because the ratio and proportions are going to be staying the same as long as you use it to eliminate a value. So if we multiply it by 3, let's write down what our new equation is going to be. And our new equation is going to be, we get, I'll just write this out here. It'll actually make it a lot simpler. We have 6x1 plus 3x2 equals, don't forget the 3 times 7. A lot of people sometimes forget that, equals 21. Now, the reason why we're doing this, and I chose 3, is because as you can see, the 3 up here, it already has a negative value. So I know when I'm going to be adding straight down in columns, you're basically, this is the direction you're going to be adding these. You can subtract as well, but I just like, if I have to subtract, I'll just multiply it by a negative, or so on and so forth. This way you don't make a mistake. Don't ever try to do math in your head. It never works out. You're not impressing anyone. Just take it step by step. And now let's just rewrite the top. So we have x1 minus 3x2 equals negative 7. Or if it makes you feel any better, let's just call it plus negative, so we're all on the same page here. So now we just want to add vertically. So what we're going to get here is we're going to get 7. Oop, that didn't turn out too well. 7x1 plus 0x2 equals 14. And simply we're going to solve for 7x1 equals 14. Just divide both sides by 7. Very simple. x1 is going to be equal to 2. So now we have x1, so what do we do about the rest? Well, what we got to do is we actually got to take our value for x2. We're going to plug this back up into here. And I'm actually just going to move over a little bit. And what we're going to get, write this down in green, is this is our first step. Second step, after you plug it in. So our second step, right up here, when we plug it in for x1, we're going to get 2. Plugging it in for the x1 over here, plus negative 3x2 equals negative 7. And what we're going to get here is we're just going to subtract 2. Subtract 2. Now you're subtracting a negative, so you're just going to get negative 9 equals negative 3x2 negative 3 divided by negative 3. The negatives are going to cancel out, and you're going to get x2 is equal to 3, and then your x1, of course, equal 2. Now, I'm just going to give you a general second sort of equation where we have three unknowns, but you're going to end up with the same solution. So what do I mean by that? Well, let's say I have 8x1 minus 3x2 equals 7. So what would I do if I plugged in, let's say, 3x1 minus 2x2 equals 0, and then we get 10x1 minus 2x2 equals 14. Well, in this case, we're basically just going to ignore these values right here. You're still only going to have two solutions because this total value equals 0. So, like I said, when we have a 0 solution, it's going to be a homogeneous system. And when you go through all this, you'll just end up with x1 equals to 2 and x2 equals to 3, the exact same as you do here through methods of elimination if we just dealt with the first two equations here. All right, there we go. That's our first example for systems of linear equations.